linear phase filter. And to make a linear phase filter, we're just going to delay our zero phase filter. And its good part is that it does not change the shape of a signal, just like that zero phase. I just want to remind everyone again, it might make the signal smaller or larger depending upon if it's in the pass band or not. But as long as you've got an entire signal that's in the pass band, it will not modify the shape at all. And if it's in the stop band, it'll change all the frequencies that are in the stop band by the exact same amount. But it is causal, and to make it, you're just going to delay your zero phase filter until it's causal. So in our example above, where this is our zero phase, and this is, wow. And this is our linear phase. It's just that. And why is that? The x, let me write it down. So the x of the linear phase of n is equal to the x of the zero phase at n minus some constant number, some delay. For this particular example we did, it was delayed by 2. And that means that our, excuse me, that means that our DTFT of our linear phase is going to be equal to our DTFT of our, let's just abbreviate it, zero phase. And what does delaying by D do to its DTFT, Jeremiah?
Nothing.
Nothing in magnitude, but it does in phase.
Oh, okay, yeah.
And what does it do to phase?
Linearly delays it.
Linearly delay. It's the same thing as multiplying it by e to the minus j here, omega d. And so now you can figure out what the phase is of our supposed linear phase system. And it's going to be equal to the phase from this. It's equal to the phase of this plus the phase of this. So this is equal to the phase of the zero phase filter plus the phase of this, which is just minus omega d. And by definition, we said our zero phase filter has zero phase. So our linear phase is just equal to minus omega d. And this is why we say it's linear phase in omega. It's a constantly, if we were to graph this thing, it is a constantly decreasing phase of with minus d. Of course, it goes only up to pi, that's true, and minus pi, and then we reset it. That's meant to be, I'm having trouble drawing. There, that's better. And then it's reset up to, again, this would be 2 pi, and it continues on like that forever. All right, so that's why we call it a zero phase, linear phase. At this point, oh, I want to compare all this with one last option, and that is our nonlinear phase.